Okay. All right, and so I think that we are ready to start. Thank you all for being here today. It is a pleasure to have you on board of this the EAGE Young Professionals community that we are going to present the first webinar of the year. So thank you, Shi Yuan, for being here today. Thank you, Bridge, also for supporting us with this presentation. For information of everyone, this session is going to be recorded, but only for EAGE. And probably this is, if you request the recording presentation, please let us know and they will see internally. We can share this with you. So yeah, I think that I'll give you the word to Bridge. Please, Bridge, go ahead.
Thank you, Maria. Thank you, everyone. Good day from wherever you are joining us, and I welcome you all to our webinar today. I am Bridge Singh, and I am currently an assistant professor at the Polish Academy of Sciences in Warsaw. I am currently also the chair for the Young Professional session. Please change, Maria. So I start with the agenda. I will give you a very short information on the Young Professional Special Interest Community, that what we did on behalf of EAGE. Then most of our session will be dedicated for the webinar. It will be followed by question and answer, and then we will finally close the session. Let me start by introducing our Shi Yuan today. Shi Yuan is currently a PhD researcher at the Edinburgh Time Lab Project Research Consortium at the Heriot-Watt University, and she focuses mainly on the CCS technique. She has been working in this field for a couple of years, and before the PhD, she was working for Icon Science for 4.5 years. She has also did her internship with BP, and where she gained a lot of valuable industry experience. Her background is very strong academic research with some practical expertise in geoscience and energy solution change. Just before the webinar, I will quickly give you this introduction on the young professional community. We are a network which is very focused on the young professionals, which means if you are 35 or below, and we are mainly interested in sharing and discussing the advice for career development, work opportunity, and the skills for a very successful career. We established in 2013, and currently we have 2,500 members. Our main platform for engagement is LinkedIn. So if you would like to join us, I encourage you all to please join us there. We are very active. If you have any comments, queries, suggestions, please feel free to drop us a message there or by email or with EG. We are always there. Change. Currently, we are a team of 12 people with different nationalities and based on different regions in the Americas, Europe, Asia, everywhere. And I'm happy to say that all of us are very active, and we have our scheduled monthly meetings where we discuss a lot of ideas. And I once again thank all of them for their work. Maria, please. Yeah. So there are many activities we do, but I would highlight just the main ones, that the Young Professional session at the annual meeting and at the GET conference. These are two very big conferences that EAGE hosts, and in both of these conferences we have a dedicated session. We mainly aim for the topics which are very relevant to the young professionals. We also collaborate with the Women in Geoscience and Engineering community. This is the second only special interest community in which we assist them, and we work with them for the EAGE mentoring program, where we try to match many mentors and mentees on different topics. The third one is the webinar series, which you are attending today. And the main thing what we focus is we share many news, what we have it. We give a lot of career advice, and we also post several vacancies that we come across, mainly on our LinkedIn page. Change. So for the mentoring program, if you are interested either as a mentor or a mentee, it is a 1-year career development program. We are not very strictly following like you have to finish like whole one year, but actually we are very flexible. We allow our mentors and mentees to interact and do the set goals within their time bound. In this, it's not mainly technical, but we focus on career, personal development. We aim different fields between industry and academia. We also have mentors and mentees seeking for work-life balance. Obviously, large part is for the technical things where students aim mainly to reach out to technical experts, but also there are like soft skill development. So we actually capture a lot of areas, and if you are interested, I highly encourage you to please visit. In case of anything, you just let us know. Change. And just I give you a small statistics that for 2025, in which our committee members work with the EAGE Women in Geoscience and Engineering Committee. And we have this year 23 mentors from Europe, America, Asia, Middle East, and Africa. So we pretty much have a very global audience. We were able to successfully match 51 mentees with them. And you can see on the chart on the right that 2/3 of them are students, but you can see that there are also like young professionals, but also mid-career professionals who are also participating in it. So it's quite a happening place. I do encourage you to have a look at it. Change. Just before I end, I would like to highlight that in this year as well, during the annual meeting of the EAGE, which is in Toulouse, France in June, we again have a new strategic panel, which is dedicated to the young professionals. And this year the topic what we have is bridging the geoscience generation gap, securing the future of the industry. So if you are attending, I invite you to please attend the session. Change. And also for the GET conference, so if it happens that you are aiming for this, we also have a dedicated session for this conference as well. And I think with this, I would now would like to give the floor to Shi Yuan so that she could today enlighten us on the CCS technique. Good luck and see you in a bit, everyone.
Thank you, Bridge.
Right. Thank you, Bridge. Thanks, Maria. Hopefully everybody can see my screen. So thanks EAGE YP community for the invitation to give a talk on exploring the role of 4D seismic in CCS, specifically monitoring CO2 injection in depleted gas fields. As Bridge mentioned, I'm currently doing a PhD within the Edinburgh Time-Lapse Research Consortium at Heriot-Watt University. We'll first start with what is CCS and why is it necessary? We know that carbon capture and storage is a critical technology for mitigating climate change by first capturing carbon dioxide emissions from industrial and energy-related sources and transporting it via maybe pipelines or ships and store it in a secure location in the subsurface. Over the last 2 decades, CCS has actually been extensively studied and discussed as a measure to reduce greenhouse gases in the atmosphere as per IPCC 2005. Now, the importance of CCS has been highlighted by international commitments, in particular the Paris Agreement, which actually aims to limit global warming to global temperature rise to 1.5 degrees Celsius. I'm sure you'll be familiar with it. In terms of the geologic storage options for CO2, we have deep saline aquifers, or we can inject them into unminable coal seams, use it for EOR or EGR, and also depleted oil and gas fields. For saline aquifers and depleted hydrocarbon reservoirs, they both offer a range of advantages and trade-off in terms of capacity, injectivity, and containment. In 2009, the IEA GHG has actually estimated that globally, the gas fields could store up to 158 gigatons of CO2 by 2050. On the other hand, the UK Storage Appraisal Project Research Consortium projected that UK alone have about 5 gigatons of CO2 that can be stored within the gas fields as indicated by this rate fraction that you can see here. Of course, the majority of CO2 will be stored within the saline aquifers, giving a rise of 78 gigatons of CO2 storage capacity. Let's now move on to the CCS activity within the North Sea. This slide actually presents the recently awarded UK North Sea CO2 storage licenses in the southern North Sea, can be abbreviated as SNS. Here we have the Viking field, Indefatigable field, Le Mans, Camelot, Hewett, as well as Vulcan. The Bunter and Endurance actually represents the saline aquifer within the southern North Sea. In this next slide, I've compiled details such as the reservoir formation, pore age, porosity, initial reservoir pressure, and then also the top reservoir depth in terms of meters reference to TVDSS for the aforementioned fields, as well as the L10 area. Broadly speaking, you can see that CCS projects in the southern North Sea are targeting the Rotliegend sandstone or the Le Mans sandstone for the depleted gas fields, and for the aquifers, we are actually targeting the Triassic Bunter aquifers. Now we'll take a look at the storage licenses awarded in the northern North Sea, which is mainly awarded in oil fields such as Magnus, Tern, Eider, and Teasel as well. So these storage sites are actually targeting the Jurassic Brand group, as you can see here. Next, we'll move on to the central North Sea, where we have the Goldeneye field. We actually target the Captain Sandstone. And last but not least, we will not forget the East Irish Sea, abbreviated as EIS, which actually has the licenses awarded to the Morecambe fields, North Morecambe and the South Morecambe, and they both target the Triassic Sherwood Sandstone. Now, the Sherwood Sandstone in the East Irish Sea is actually equivalent to the Bunter Sandstone in the Southern North Sea. You'll notice at the front is that the top reservoirs for the Morecambe fields are actually pretty shallow. They're less than 1 kilometers, and they also have quite low porosities and low pressures as well, being such a shallow reservoir. Now we'll move on to the licenses for carbon storage within the Norwegian continental shelf. So until now, a total of 13 storage licenses have been awarded for CO2 storage in the Norwegian continental shelf. In total, there's one exploitation license, as indicated by this legend here, and there are 12 exploration licenses. Now, exploration licenses are typically offered to companies that have presented good plans for the development of CO2 storage, and it's typically given prior to awarding an exploitation license in the relevant area. Exploration licenses can be awarded to one or more competent companies. On the other hand, having an exploitation license provides an exclusive right to store CO2 in the area covered by the license. You notice in this figure, I've included the Barents Sea at the top north, Norwegian Sea, and also the North Sea. So this is the Norwegian sector of the North Sea, unlike earlier we've seen the United Kingdom sector of the North Sea. So if we focus on the North Sea, there's two areas, Area 1 and Area 2, and this is just a blow-up of them. So here we have all the exploitation and exploration licenses. The only exploitation license is right here in the middle, and the rest over here are the exploration licenses. And next up, we have one area in the Barents Sea, and that's pretty much it. These are information that I've actually extracted from the Norwegian Offshore Directorate, NOD, as you can see here. Now let's move on to MMV planning. We have actually seen quite a bit of activity going on in the North Sea, which is actually not surprising given the net zero initiatives set up by the government. To ensure the safety and effectiveness of these efforts, the operators actually must establish strong and robust monitoring, measurement, and verification programs, MMV. So MMV essentially is one of the central and visible parts of safe CCUS operations. I've extracted here Article 13 and Article 14 from the EU CCS directive on geological storage of carbon dioxide, which is actually the main piece of regulation for CCS across Europe. The high points of these two articles include detecting migration of CO2 and detecting leakage of CO2. In addition to that, we're also interested in the frequency of monitoring and the technology to be employed. When you put all of this into context and define the purpose of an MMV, you can divide it into two. First, it will be containment monitoring, which is to ensure the injected CO2 remain within the storage complex for long-term storage. And second, we have conformance monitoring, to ensure that the storage complex is behaving in a predictable manner and it is fully consistent with the subsurface model. Containment monitoring can actually be further divided into volumetric estimates of the CO2 and also understanding and ensuring the cap rock integrity. While conformance monitoring, on the other hand, can be further subdivided into understanding the lateral movement of CO2 front and also the calibration of the predictive model. The natural next question is, we understand the importance of MMV, but what should we use to monitor? So here I've presented a variety of time-lapse monitoring techniques along with their capabilities and limitations. From top to bottom, we have 3D and 2D towed streamers, which has high detection and also resolution capabilities. 3D streamers actually lack azimuthal variation, and the interpretation is actually highly dependent on repeatability. While 2D streamers lack 3D migration. P cables, on the other hand, which is a variation of the towed streamer, is suitable for shallow depths, but it's susceptible to multiples, and also it's highly dependent on sea conditions. The limitation of conventional towed streamers actually motivated alternative technologies such as ocean bottom nodes, abbreviated as OBN, and ocean bottom cables, abbreviated as OBC. Now, both OBN and OBC are able to provide wide azimuth coverage, but it has limited sampling density. OBN is more suited for shallow depth, and OBC is more suited for deeper areas. In addition to these, we also have vertical seismic profiling, sometimes also known as VSP, which gives us high resolution near the wellbore, but it comes with a downside of having non-uniform coverage. The most recent technology would have to be focus seismic, where it actually utilizes one source and one receiver to retrieve subsurface information. It is cost-effective, but it has a small coverage. And also where you plant the focus seismic areas is also very highly dependent on your simulation model being very accurate. For today's discussion, we will narrow down to only towed streamers and OBNs, or rather seismic in general, instead of focusing on VSP and focus seismic. Right. So let's take a look at the study I've done for the Goldeneye field, Hamilton field, and Viking fields in the North Sea and the seismic modeling outcomes. I have picked these three fields as my case studies for the simulation to seismic modeling work. Goldeneye field, located in the central North Sea, with Captain Sandstone as a storage site, Hamilton Field located in the East Irish Sea with HyNet Northwest project as the CCS project, and the storage site as the Ormskirk Sandstone. And lastly, Viking Field in the southern North Sea, and it will be in relation to the Viking CCS project or the VNet Zero project, where the storage site is the Le Mans Sandstone. Now, I've picked these 3 fields because these are real projects that's meant to comment in the next few years. Note that the simulation models that I've actually received for these 3 fields are not exactly the same as the operators, but these are valuable nonetheless, as it gives us an understanding of what might happen to the reservoir when we inject CO2 into the system. Also note that the timeline of CO2 injection that I'll be presenting in the next few slides, and the injection rates might differ from the actual CCS project when they commence. In this next slide, I've included key information of the GoldenEye field, Hamilton field, and Viking fields, with the storage site first, average porosity, the initial reservoir pressure in terms of MPa, reservoir temperature in degrees Celsius, and the thickness. Now, these are all important information, especially the pressure and temperature, as this will determine if the CO2 will be injected in a supercritical phase or a gaseous phase, and the thickness and the porosities are one of the factors that will influence the detectability of seismic. Right. Now we'll move on to the next slide. So I've conducted comprehensive simulation to seismic modeling, can be abbreviated as SIM2SEIS, to get a better understanding of the pressure and saturation changes that is needed for effective 4D monitoring. This can be split into first simulation modeling, where I've collaborated with reservoir engineers to build a compositional simulation model for the GoldenEye field. And the models of Hamilton and Viking simulation models were kindly donated by Axis Well Technology as part of the UK Storage Appraisal Project, UK SUP. Next, I'll use the simulation model to convert it into a petroelastic model, where I've calibrated the petroelastic model so that it captures the lithological variation and pressure effects on dry rock frame. In addition to that, I've also computed the fluid properties using the Sutton and Harmon 2009 empirical relation. Next is synthetic seismic generation, seismic modeling. Basically, it involves converting the outputs of a petroelastic model, which is typically a P impedance volume, and convolve with an appropriate wavelet to give us a synthetic seismic. And this can be repeated at multiple time steps to then create what we call time-lapse or 4D seismic. When we inject CO2 into the system, some might expect CO2 to be present as a separate phase from the brine, hydrocarbon gas, and oil. However, in reality, it's that when we inject CO2 into the system, this the CO2 actually mixes with the existing reservoir fluids, so it would form new mixtures. For example, CO2 dissolved in brine, CO2 mixing with hydrocarbon gas, and CO2 dissolved in oil. Now, these new fluid mixtures can be computed using either an equation of state, abbreviated as EOS, or published empirical relations. Whereas these four as separate fluids, they can be computed either using Bezel and Wang, Fleck, or NIS. Now, this new mixtures, it's very important because this forms a fundamental step to give rise to the single effective modulus that we will then input into Gasman's equation, which is basically the key for any type of modeling work that we'll be doing. If we kind of take a step back and compare the differences of SIM2SEIS in the oil and gas domain versus SIM2SEIS in CO2 injection domain, we can pick out what the differences are. So the main steps would be the simulation model, petroelastic modeling, and seismic modeling. In the oil and gas space, we typically use a black oil model to build our simulation model. And the output of the black oil model is actually gas, oil, brine, in addition to the other dynamic properties. We can then convolve this with a wavelet to generate the synthetic seismic. On the other hand, when we introduce CO2 into the system, it actually requires a compositional simulation model to capture the nuances and the complexity of CO2 mixing with the reservoir fluids. And here is where we'll notice the difference, is that a compositional simulation model will actually give fluid component outputs. For example, the vapor mole fraction and liquid mole fraction of CO2, in addition to the other fluid components that might be present in the reservoir. We also get the gas, oil, and brine, similar to the black oil model. And once we have this, we can calculate our P impedance volume, convolve with a wavelet to get our synthetic seismic. So the main differences is what simulation model we are using, whether it's a black oil model or a compositional simulation model, and how we can compute our fluid properties. Like I mentioned, here we would require the vapor and liquid mole fraction of the different fluid components, where this we can just get by with Batson-Wang flag on this. So all in all, both methods, the petroelastic modeling phase is where the differences is, and the seismic modeling phase remains the same. This is a good slide that I've actually borrowed from Jorge Landa within our ETLP group to explain what actually happens when CO2 is dissolved in brine. You see the solubility of CO2 in brine will actually be highly dependent on the salinity in brine itself. The more saline it is, the less soluble CO2 will be. And if CO2 does dissolve in brine, it actually changes the density and the velocities, or rather the speed of sound, as shown on the two plots on the right-hand side that you can see here. You see that CO2 actually decreases the density of brine as it is lighter, and at the same time, it also decreases the speed of sound, which is velocity. And the velocity and density of this new fluid mixture, which I call CO2 dissolved in brine, is actually a function of pressure, temperature, the solubility of CO2 in brine, as well as the salinity. And these can be calculated using the references here, which the main one would be the Hans equation, 2013. Next, we'll look at this next slide, which I also borrowed from Jorge Landa, and this gives us an understanding of what happens to the density and velocity when we allow CO2 to mix with hydrocarbon gas. Basically, when we mix CO2 with hydrocarbon gas, it actually increases the density, as shown in the left-hand plot, as CO2 is heavier than hydrocarbon gas, but it decreases the speed of sound, as shown in the right-hand plot. Now, this new mixture composing of the hydrocarbon gas and CO2 can be computed using empirical relations such as the Sutton's relation that you can see here. And it is a function of the pressure, temperature, gas mixture gravity, the CO2 mole fraction, H2S mole fraction, and also the N2 mole fraction, if these fluid components are present. To help you kind of visualize the outputs of a compositional simulation model, I've included here a cross-section of a compositional simulation model for the GoldenEye field to help you visualize the different components present. To the left, we have the gas saturation at pre-CO2 injection conditions, 2016, and to the right, we have the gas saturation at post-CO2 injection, 2022. If I pick this particular cell, you notice that it is mainly made up of C1 and 2, and this is the 6 fluid components present within the compositional simulation model. At 2016, it's mainly made up of C1 and 2, and when we inject CO2 into the system, the mole fraction of CO2 actually increases to 76%, which is also this particular same cell that we see. Right, so now let's move on to the applications into these three fields. Let's first start with the GoldenEye field. This slide actually shows the life cycle of GoldenEye field first as a hydrocarbon producer and then its second life as a CO2 storage site. The plan was to inject 1 megatons of CO2 for 20 years commencing from 2016, which gives us a total stored volume of 20 megatons of pure CO2 in the Captain Sandstone. The phase diagram on the bottom left actually shows that CO2 is injected at supercritical phase throughout. As you can see here, the pressure and temperature conditions is indicated by the orange star, and the pressure and temperature conditions of the CO2 is indicated at the green star, as you can see here. On the bottom right, I've included a cross-section of the GoldenEye field. You notice that Captain D sandstone has the best reservoir qualities, and this will be where we'll be storing the the CO2s into the Captain D sandstone. This slide shows the 3D seismic modeling slides for GoldenEye field. So the top panel actually shows the porosity, pressure at baseline conditions, and the saturation tertiary diagram at baseline conditions. And the bottom panel actually shows the 3D seismic cross-section at baseline conditions, which is 2016, and arbitrary monitor 1 condition, which is midpoint of the CO2 injection, 2026, and at the end of CO2 injection, monitor 2, which is 2036. Right. Now we are more interested in the 4D effects of it. So for the purpose of this study, I've actually modeled the individual effects of pressure and saturation. Let's start by evaluating 4D signal due to rock and fluid pressure effect. The top panel shows the changes in pressure for 1 year of CO2 injection, 10 years of CO2 injection, and 20 years of CO2 injection. The bottom panel shows the corresponding 4D quadrature amplitude due to pressure effects only. So you can see that at the end of 20 years of CO2 injection, we have 7 megapascals of overall 7 megapascals of increase in pressure, which is not a lot, and the corresponding 4D quadrature amplitude due to pressure effects only is actually quite subtle, and I had to boost the color bar by a factor of 2 to have it consistent with the 4D signal or 4D quadrature due to saturation effects that we'll see in the next few slides. In terms of the 4D signal due to saturation effects, we first take a look at the changes in gas saturation. You notice that as we inject CO2 into the system, there's also an increase in gas saturation, which is pushing down the water ingress from the crest of the structure. And then at the end of CO2 injection, you can see that it forms, from the original gas-water contact, it forms a new fluid contact, which I now term the CO2 gas-water contact. The bottom panel here actually shows the 4D quadrature due to saturation effects. And as you can see, we have a booming signal at the end of 20 years of CO2 injection at the fluid contact. Now, gas saturation composed of all the fluid components that we've seen earlier, which is 6 different fluid components. So we'll need to look at the changes in vapor mole fraction to actually see where CO2 is actually flowing. The first thing that you'll notice is that CO2 is indeed dominated by gravity, and how it flows is that it will flow along a high perm layer, and it will broadly speaking, it will actually sink to the bottom because it is denser than the other fluid components. And the bottom panel that we see here is the 4D quadrature due to saturation effects, which is similar to what we've seen earlier. Lastly, we'll take a look at the changes in P impedances, which can actually serve as a quick look if one does not have the time to go through with the full seismic modeling. Overall, we see a softening effect over here as CO2 is replacing water, and when the hydrocarbon gas CO2 mixture starts to displace water into the aquifer, that is where we see a dark red response of about 10% decrease in P impedances. And it's about 2% decrease in P impedances as you're pushing water from the crest of the GoldenEye field. And this hardening response that you see here of about 2%, it's actually CO2 dissolution in the oil rim. There's a thin oil rim in the GoldenEye field, as GoldenEye field is actually a gas condensate field. It's not a dry gas field. Overall, the main takeaway is that the 4-day quadrature amplitude due to saturation effects can be quite large, 10 times the magnitude of the intra-reservoir signal at the fluid contact compared to the intra-reservoir signal. Now we'll move on to the second field, which is Hamilton field. So Hamilton field is actually a host block structure located in the East Irish Sea, and the storage development plan of the Hamilton field has been configured to service a CO2 supply of 5 megatons of CO2 over an operational lifetime of 25 years, giving rise to 125 megatons of CO2 stored in the Ormskirk sandstone. Now, the first thing you'll notice is that Hamilton field has a very low pressure, being a shallow reservoir. So CO2 will initially be injected as a vapor phase for the first 13 years until sufficient reservoir pressure has been reached to support the supercritical injection for the remaining 12 years. And the bottom right figure here actually shows the different zones in the simulation model: OS2B, OS2A, OS1, and SAN-Bs making the base of the reservoir. The slides are actually designed in the same format, where we have porosity, pressure, and saturation at baseline conditions, and the bottom panel actually shows the 3D seismic at the different time steps. So this is 2026, 2039, and 2051. So unlike the GoldenEye field, there's actually a little bit more pressure buildup of up to 11 megapascals at the end of 25 years of CO2 injection. And it was actually understood that all Hamilton production wells perform similarly and arrived at similar depleted pressures, which indicates that there is good connectivity in the reservoir, implying that the infill faults that you see here are actually non-sealing. The 4D signal due to pressure effects only is observed to be moderate and present throughout the reservoir interval, unlike what we've seen in the GoldenEye field. Now let's move on to the saturation effects. Let's take a look at the changes in gas saturation. Notice that the original gas-water contact is pretty flat here, unlike the GoldenEye field, and there's not much movement after 25 years of CO2 injection. There is a lack of aquifer influx and minimal pressure support within the field during production, which suggests that Hamilton field is actually a closed system. And in terms of the 4D signal due to saturation effects, we can observe that it is quite subtle and it's present throughout the reservoir interval. Due to the lack of fluid contact movement, we don't really see a booming signal as what we've seen in the GoldenEye field. However, if you look in terms of the changes of mole fraction, changes in vapor mole fraction of CO2, it is actually quite the contrast to the GoldenEye field. As after 1 year of CO2 injection, you notice that CO2 immediately mixes with hydrocarbon gas throughout the reservoir interval. So this is quite different from what we've seen in GoldenEye field. Now let's recall a couple of things, which is that CO2 was injected as a gaseous phase via 2 large injection wells, as you can see here, and the injection wells with large injection area, and also the injection rates in Hamilton field were much higher compared to GoldenEye field. It is 5 megatons per annum in Hamilton field versus 1 megaton per annum in the GoldenEye field. Similar to the GoldenEye field, we also observed the denser CO2, or the bulk of the CO2 will be sinking to the end of the high perm layer that we see here. Lastly, if we look at the changes in P impedances, it's not too exciting if I have to be honest. We observe a hardening effect of about 1.6% due to the mixing of 2 gases, which is basically hydrocarbon gas and CO2 mixing. We do not see any pushdown effect into the aquifer, therefore no booming signal in terms of 4D signal due to saturation effects. Lastly, we have the Viking fields. So the Viking fields were some of the earliest discoveries and developments in the southern North Sea, and it's actually comprised of a number of accumulations within separate fault compartments, as you can see in the bottom right here. For this study, Viking A was actually selected as the primary storage complex as it has the largest storage capacity. The development plan has been designed to accommodate 5 megatons of CO2 injection into the Le Mans sandstone for 26 years, starting from 2031, giving rise to 130 megatons of CO2 stored in the Le Mans sandstone. Similar to the GoldenEye field, CO2 will be injected and remain at supercritical phase throughout the 26 years of CO2 injection. This slide shows the three productive sand layers that we can see here, A, C, and E, that will be targeted for the CO2 storage. Now, these units are actually separated by laterally extensive non-pay units, also known as the subcar silts, that actually acts as horizontal barriers to vertical flow. Communication between the sand units does occur when the sands are juxtaposed at internal faults. The top panel, we can see from left to right the porosity, pressure, and saturation tertiary diagram at baseline conditions. And the bottom is the 3D seismic cross-sections at the different time steps, 2031, 2043, and 2057. Now let's take a look at the 4D signal due to rock and fluid pressure effect. The overall pressure increase in Viking field is much larger compared to the previous two fields, reaching a maximum of 34 megapascals. It was 7 in GoldenEye field and 11 in Hamilton field. This large pressure increase actually is reflected in our 4D signal due to pressure effects only, where we observe a reasonably strong 4D signal at the reservoir interval. And in terms of the 4D signal due to saturation effect, we can see that similar to the GoldenEye field, there is also a push-down effect into the aquifer to form the new fluid contact, the CO2 hydrocarbon gas fluid contact, and this gives rise to a booming 4D signal at the fluid contact. In terms of the changes in vapor mole fraction of CO2, we see that the injection belt actually perforates all the sand units. Therefore, we see sand flowing into all the three units. And in particular, it's flowing the quickest in sand unit A, as it has the highest it has a thin layer of high permeability, allowing for CO2 to flow quicker. The bottom 4D quadrature amplitudes due to saturation effects remains the same as we've seen previously. And lastly, we have the changes in P impedances for Viking field due to saturation effects only. We can see here that the hydrocarbon gas CO2 mixture pushing down into the aquifer actually gives a reasonably large decrease in pre-impedance, being 9%. And this is actually quite similar to what we've observed in the GoldenEye field, which is about 10%. Whereas the mixing of the hydrocarbon gas and CO2 is only about positive 0.3%, which is slightly lower than what we've observed in Hamilton, which is 1.6%. Overall, for the Viking field, we observe that the 4D signal it's really large and really observable at the fluid contact, being at a magnitude 9 times larger than our intra-reservoir signal that we see here. Now, this is a summary slide comparing the three compositional simulation models. Hamilton field and Viking field were actually structured to accommodate larger injection rates. Therefore, it has larger stored volumes, as you can see here. And because Hamilton field has a very low pressure, it will go through a dual injection phase, where CO2 will be initially injected as gaseous phase before it turns to supercritical for the remaining 12 years. GoldenEye field is connected to the neighboring aquifers, therefore the maximum pressure increase is pretty low, it's only 7 megapascals, while Viking field observes the largest increase in pressure being 34 megapascals. Right, Now, this is basically a slide comparing our observations of 4D signals. On the left, we have the pressure signal, and on the right, we have the saturation signal for the GoldenEye, Hamilton, and Viking field. All of these seismic cross-sections actually have been normalized by the geology and have a similar color bar to facilitate comparison. So if you look at pressure signal first, Viking field, which has the maximum pressure increase, has the largest pressure signal. This is not surprising. And in terms of the saturation signal, in Hamilton field, we only observe CO2 and hydrocarbon gas mixing. Therefore, it has a very subtle intra-reservoir signal. On the other hand, GoldenEye and Viking field actually observe the hydrocarbon gas CO2 mixture pushing down into the aquifer. Therefore, it causes a booming signal at the fluid contact, and it has a slightly weaker intra-reservoir signal. So, the 4D signals due to saturation effects can actually be split into two. Let's first start with the intra-reservoir signal. From left to right, I've actually displayed the tertiary saturation diagram at baseline conditions for the Viking field, the impedance change after 26 years of CO2 injection, and the corresponding 4D quadrature amplitude. If we focus in the gas lake, here you notice that even though as we inject CO2 into the system, the density increases, but the velocity acts in the opposite direction, giving rise to little changes in P impedances, and therefore effectively cancelling each other out, giving rise to a subtle hardening signal at the gas lake. However, if we look at the fluid contact signal, it will be different. If we focus on the water lake, as you can see here, when the hydrocarbon gas CO2 mixture actually pushes down and encroaches into the aquifer, the density and velocity act in the same direction, decreasing substantially, contributing to a strong softening signal that we observe at the water lake, as you can see here. The analysis of CO2 storage monitoring reveals several key aspects of seismic responses. The first thing is that there are two fundamental response mechanisms, the intra-reservoir signal, due to intra-reservoir fluid composition changes, and the fluid contact signal, where the hydrocarbon gas CO2 mixture actually displaces water or encroaches into the aquifer. The observations is that the contact-related signals demonstrate 10 times greater strength than the intra-reservoir signal in terms of the amplitude and the P impedance as well. Even having this, we still remain several key technical challenges, which is that pressure effects can actually substantially mask saturation signals, making interpretation more complex, and the magnitude of pressure response actually remains the primary source of uncertainty factor in these assessments. Additionally, reservoir heterogeneity emerges as a critical factor in determining the patterns of saturation responses, and therefore there is a need for detailed reservoir characterization in the monitoring strategies, and we'll need to have an appropriate simulation model to understand the responses. This is the conference proceeding that I've mainly used for my talk. You may scan the QR code for this. And also, I would just like to end the presentation with several resources that I find it very helpful. To the left, it's the CCS Directive Guidance document, which is the EU CCS Directive for MMV planning. The middle one is the UK National Data Repository for all information in regards to the UK sector of the North Sea. And to the right, we have the public data for the Norwegian sector or the Norway sector of the North Sea. I would like to acknowledge some of my colleagues. First is Colin Macbeth for the supervision, simulation modeling for Axis Well technology, Gillian Pickup and Rasul Amiri for helping to build the GoldenEye model, fluid modeling for Jorge Landa, and also the petroelastic model calibration for Hamid Hedari. You may learn more about the ETLP Research Consortium at Heriot-Watt University by scanning this QR code. It brings you to our website. Lastly, I would also like to acknowledge the ETLP sponsors, Phase 8 and Phase 9 sponsors. There's about 20 of them for funding the research consortium, which allows me to study. And that's pretty much it. This is a list of references for your perusal. And yeah, you may also scan this QR code to join us on the EAGE Young Professional community at LinkedIn. I guess now I can open the floor for questions.
Yes, for sure. Thank you, Shi Yuan Toh, for this amazing talk. So I think that I have a couple of questions that some attendees shared with us previously. Maybe we can start with this one, and then if one of the audience or the attendees have any question, you just have to turn on your microphone and ask directly to Shi Yuan. So let me start with the first question of this. Data-driven applications in CCS for the CO2 behavior feasibility x real data. What are the main challenges associated with using 4D seismic for CO2 monitoring, and how can they be overcome?
All right. I guess let's start with the first, which is the data-driven applications. So basically, in my talk, I have focused mainly on 3 fields within the North Sea: Goldeneye, Hamilton, and Viking fields. So these are all, or rather, these are actual field data. This is not just theory and building a simulation model, like a box-like simulation model. This actually incorporates the geology. Uh, so this is the ones that I've done simulation to seismic modeling on. In terms of other fields that I've studied, that this actually includes 64 fields within the UKCS and NCS. UKCS being United Kingdom Continental Shelf and NCS being Norwegian Continental Shelf, which makes up the entire North Sea. So I have studied 64 fields, but that's just a single data point analysis. Using field-specific information such as the field-specific pressure, temperature, gas gravity, to find out the optimum, or rather the most likely 4D response if we use such and such porosity, which I have actually presented in, I think, last year's EAGE, and there's also a conference proceeding on that. If anybody would like to check it, you can DM me on LinkedIn, and then I could just send the paper over if that's interested. And I think, Maria, you had the second question. I think I just answered the first part. Like,
Okay,
if you want
so
to
the
repeat.
second is, what are the main challenges associated with using 4D seismic for CO2 monitoring, and how can they be overcome?
Right. So, what are the main challenges? I think that there's a lot of challenges with using 4D seismic. I guess there are two parts to it. One is the technical challenges, and there's the other part, which is the economic challenges. So we know that 4D it's not necessarily the most cost effective, or I wouldn't say cost effective. It's not the cheapest way to monitor. There are of course cheaper alternatives. For example, gravity, or just like wellbore monitoring, which is much cheaper than a actual 4D survey. But I feel that 4D is perhaps one of the techniques that's able to give the best resolution and a much wider coverage than, for example, a DAS VSP. So throwing back to this challenge question is that I think one really have to determine the cost versus value, and from there kind of decide what is the objectives and which is the most appropriate method to go about it. Because it doesn't just have to be 4D seismic, it could be a hybrid solution, meaning you could acquire a baseline which is using seismic, and then maybe after 10 years you can acquire another seismic, but intermittently you could potentially use gravity, or you could potentially use focus seismic to kind of trigger another 4D seismic or 3D seismic at a different time, which becomes 4D seismic. And yeah, so I feel like to this is not a simple question to answer, and there's a lot of more questions that would help with the deciding if it's worthwhile.
Thank you, Shi Yuan. Third question, are there case studies or examples where 4D seismic has played a critical role in ensuring safe and efficiency CO2 storage?
So for the seismic, so this question is not in particular to gas fields. We have seen that 4D seismic has played a huge part in your classic example, which is Sleipner. So it has, but that's an aquifer. So it has played a huge part for monitoring CO2 injection in aquifer. I think that in aquifer that it has pretty much proven its value, but for other places such as like gas fuels or even oil fuels, I think that we have yet to see the full value of this yet, simply because we have not done it. Currently, it's all feasibility studies. Until companies actually start injecting and until companies actually start acquiring seismic, we cannot prove or deny whether or not the methodology works.
Thank you. The other question. What role does real-time 4D seismic data play in decision-making processes during the CO2 injection phase?
Real-time 4D and decision making?
Yes.
Right. I do think that this real-time 4D for CO2 injection, I don't think anyone has done that yet, especially because first of all, for 4D, just one 4D as not a real time, just like a one time shoot, it's already pretty expensive. So I've not seen anyone done that yet. I'm pretty sure it would give very good value, but then again, this prompts for the future project that has not commenced yet. And perhaps one of the interesting things that I could share is that I've heard that Perenco in the North Sea, they are using real-time focus seismic for the first 5 hours of CO2 injection to observe the pressure kick. And I think this now ties back to the objectives and what are you looking, what's the benefit and value that you're trying to get out of 4D. And for Perenco's case, they're interested in observing the pressure kick, and they've opted to use focus seismic. It would be really interesting if the data gets becomes public, or if they present at conferences to actually observe that. But I've not personally, to my understanding, like, and to my knowledge, I don't think anybody have done that. I think it could be of good value, but again, there's the economic considerations as well.
Thank you. Last question. What additional technologies complement 4D seismic in ensuring that CO2 storage sites remain safe and compliant with environmental regulations?
What techniques complement 4D seismic?
Yes.
Yeah. So I honestly think all techniques complement 4D seismic, and every technique out there, yeah, it has complements. There's, you can think of gravity, you can think of dust VSP, you can think of like traces. Everything complements 4D seismic. It's just to what are you trying to address specifically, and then you should do your, again, this cost versus value ranking to determine which technology suits best for what objective. So there's a plethora of techniques complemented. And I just wanted to point out that is that 4D seismic is not just seismic. There's also, like I mentioned earlier, there's towed streamer, there's variation of towed streamer, for example, P cable, short cable, long cables. There's many variations. There's also ocean bottom technologies to that as well. And there's also permanent reservoir monitoring systems. So these are all everything complements. Well, I think everything can complement 4D seismic, but falls back to the economic decisions, I feel.
Thank you, Shi Yuan. There's some more questions in the chat. Sanhif, if you are still here, maybe you can turn on your microphone and ask directly to Shi Yuan.
Hi.
Please go
Hello.
ahead.
Yeah, I already
Hi.
written over there. Hi. So, like, it's something like, uh, so if like we have to do 4D seismic for carbon capture storage mainly in basalts. So it will be required to acquire the data multiple times after certain interval of time, right?
Mm-hmm.
So let's suppose we injected the CO2 within the reservoir. So after how many years the second phase need to be uh, record again? Next phase of recording for the 4D seismic data is required.
To my understanding, this is something that needs to be done. It's part of a study to identify whether or not the second phase, like when how much CO2 is needed for visibility, and you know what it's, whether it's seismic, whether it's dust, and yeah. For me, the first thing would be to do a feasibility study, do a simulation model, conduct a feasibility study for, be it seismic, VSP, or whatever monitoring technology you need, and then to do a sensitivity analysis, because the regulations, everything is case dependent. Everything is case dependent. There is no one, to my knowledge, there's no one regulation that says that, oh, after every 5 years you should acquire the data. You you might be able to do that, but you might not be seeing anything, which then is, you don't get the value out of your costs, right? You don't get your value out of the cost. And there's also like a lot of things to think about, because I think you're talking about basalt. I myself is not
Yeah,
familiar with basalt. It's not within my scope. I'm focusing mainly on clastics.
yeah, yeah.
So the first thing you need to think, it's, or to see, is understand it all boils down to fluid compressibility, which means like whether your fluid is compressible or not, and also the stiffness of the rock. So if your rock is really stiff, and if the fluid compressibility is not high enough or not low enough, then it's just not detectable, and therefore you should opt for an alternative method. But yeah, I think there's no one straight answer. It'll be project dependent, and you will require modeling to properly understand.
Right, right. So apart from this 4D seismic, is there any other technology in your knowledge which we can adopt for the monitoring of injection operation?
Injection of pressure. All
Yeah,
all other technology, you could understand injection of pressure. You could do like gravity. You could also like subsidence monitoring, seafloor deformation. There's a lot of things, but it all requires you to have a good geomechanical model to understand
no,
what
but
you're seeing.
that will not give the real time, right? That will not be possible in
Well,
real time.
sorry, I don't. In real time,
So that,
well, there is
yeah,
there is real time monitoring. Like
yeah,
I guess now it goes down to the contractors if they offer such real time monitoring. To my knowledge, is that contractors do offer real time monitoring, but I've not seen real time monitoring for CO2 injection projects, because there's not too many CO2 injection
yeah.
projects
That's why
that
it's
have
a,
this
it's a
kind of,
very new
yeah,
technology. Yeah,
yeah.
right. Okay, thanks,
Thank you.
Thank you,
thanks, Ron.
Sanjeev. Any
Yeah.
other question from the attendees?
Hello, can you hear me?
Yes, please go ahead.
Yeah, thank you for the presentation. A quick question. How do you calculate the pressure signal from laboratory analog? You only increase porosity, so only increasing the porosity, and that's it.
So thanks for the question. Hold on, just lab analog and pressure. So basically what we would have is, we would have the dynamic property from the simulation model that would give us the amount of pressure increase. When I put in brackets laboratory analog, it means how much of this pressure I'm actually translating it into 4D signal. if that makes any sense. So for example, in the North Sea, different type of rocks has different sensitivity towards pressure, and therefore different pressure have different sensitivity towards the velocity, which then gives us our seismic amplitudes. And when I'm using this laboratory analog, it simply means that I've go into a data set, which is basically the Macbeth 2004 paper. I go into the catalog. I pick an average porosity based on the average field porosity. Let's say, for example, GoldenEye was 25%. And then I go into the catalog to check if there's a North Sea lab example that it's also 25%. And then I'll use it to then calibrate my pressure signal, if that makes any sense. I'm not sure if I really answered your question well.
No, thank you. It's an interesting way to address of this problem, because I understood that it's the main challenge, understand what is pressure signal and what is saturation signal. So very, very interesting.
No, yeah, it's a pressure signal is something that people are generally concerned, but for my case, I'm studying pressure signal within the reservoir. People tend to study pressure signal for the geomechanics and the overburden, which then say like how much, what's your drilling window, how much your rate should be. So there's different types of concerns towards pressure signal, and also like whether it's in the reservoir or out of the reservoir. So some food for thought for you as well.
Thank you. Thank you so much.
Thank you.
If I can ask a last question,
Yeah.
how about the maximum frequency modeling for the seismic? I mean, do you use like a trial and error for choosing the maximum frequency, or is there any other standard that you use?
When you talk about maximum frequency, are you referring to the frequency of the wavelet or the maximum frequency?
Yeah, of the wavelet and of also the finite difference as well, modeling.
Right. So in terms of so how it works with the wavelet is I go into the public domains, which is I've mentioned earlier just now, the UK National Data Repository or the Norwegian Offshore Dictionary, and I would try to get the seismic data, and then the exploration seismic data. So from there, I would pry out the frequency domains and the bandwidth from the existing seismic data from that area, and that's how I use it for my seismic modeling. So the whole purpose of this study is to actually, which I've not fully shown case, is to actually make my synthetic seismic generated more like actual seismic. And yeah, that will be hopefully a different presentation. So yeah.
Okay. Thank you very much, Shi Yuan. Thank you.
Thank you.
Thank you, Salvatore. Any other question from the attendees? No more questions so far.
I think I can ask one to Shi Yuan.
Yes, please, Bridge.
Okay.
Yeah. Okay, there is someone asking, but I was, if I understood correctly, Shi Yuan, that you are doing the modeling and it's mainly pressure, right? So you are mainly in the acoustic approximation. Did I get it right? So this is like a very large, I would say already an approximation, because you are modeling your pressure thinking it's an acoustic medium, but in reality it's elastic. So we are already approximating, and then most of our results are based on this acoustic approximation. So how do you, when you do the model and you are coming up with these different pressure values, then how do you like kind of QC it that what you're approximating with this acoustic approximation is like within like realistic range? Like, do you like use some other data? What kind of other results or other information that you use? How do you do it?
So let's see. So based on the Macbeth 2004 paper, he would in his catalog, there is what are the typical velocity changes or like acoustic changes that you're supposed to get, right? So that's one way of QCing if my pressure changes are realistic or not. The second way is to basically just convert them to time shifts, and because time shifts is also another attribute that we use within the time-lapse community to actually understand it's just another time-lapse attribute. So the other thing is to just convert that to time-lapse attribute and see for example how much pressure depletion and how much time shift we would get. So this is like how much pressure increase and what's the time shift that we get, and use that as like a ballpark figure, if that makes any sense.
Okay, I see. I think I should get first to the Macbeth paper, probably. Then we'll come back to you. Yeah, I think there is another
that is
question.
it's a good paper.
There's
Yeah.
another question into the chat from Noor. What are the key challenges and benefits of using 4D seismic monitoring to track CO2 movement and storage in depleted gas fields for carbon capture and storage, CCS applications?
All right, so it's specific to gas fuels. So the key challenge, it's basically pretty much what I shown. For example, in Hamilton field, you really can't see anything in Hamilton field. So it would be challenging if you don't see a fluid contact movement. That is where 4D seismic monitoring would not be the best tool. But then if you go back to the MMV objectives, there's the containment monitoring and conformance monitoring. So in terms of containment monitoring is, to check if the CO2 is within the model. So I would say that 4D seismic is perhaps not the most suitable for containment monitoring if there's no fluid contact movement. However, for conformance monitoring, when it has leaked out or it has left the storage site for one reason or another, 4D seismic will work. So that is where I will put the applications of 4D seismic for gas fuels in particular. The benefit of using 4D seismic, it's honestly the coverage and the resolution. It's superior in that sense to other technologies, because for example, wellbore monitoring, you only have a single well, and it would be good if you're looking at near wellbore problems like geomechanical problems or like understanding the Joule-Thomson effects and stuff like that. It will be helpful, but that doesn't give you a comprehensive monitoring. So if you were to go back to the MMV and also like to fulfill the legal requirements from the legal documents, then I would say one way or the other 4D seismic should be part of it. Whether or not it's a frequent part of it, it's a different story, but the baseline should be there. So once you have the baseline, then you can decide if intermittently you want to do something else like dust or gravity that is much cheaper than 4D seismic. Hopefully that answers your question.
Sorry, Guhan, I have a last question. I would like to ask you, is it possible that this 4D seismic can be useful for geological sequestration of CO2 into basalt as well?
So I am not familiar with basalt, and therefore I can't really give a good answer whether it's
Okay.
whether it's suitable for basalt or not. But
Okay.
what I would
Okay.
think immediately at the top of my head is that for me, factors that are important for 4D seismic to work, because 4D seismic is both velocity and density, is that
Yeah.
you need the contrast of the displacement of fluid to be big. If there's a fluid
Right.
replacement program, if that makes any sense. Meaning if it's gas mixed with gas, then the contrast would be small. If it's gas pushing water out, then the contrast would be big. If that happens within basalt, then yeah, that is the detection limits of 4D seismic. And then I think basalt is,
Yeah.
to my understanding, is just a different
From
rock frame.
geological point of view, yeah, from geological point of view, basalt is very reactive rock. There is a plesioclase is there, olivine is there, and it can be highly reactive with the carbon. So that's why
Right.
there is an idea that in many places that basalt can be the good reservoir for the for this CO2 injection. So we are working on that. So that's why my question is, I'm also thinking that what are the other methods we can apply. So that's why I'm attending this your webinar very consciously, right?
No, yeah,
So
of course.
anyway, like you think your way, you can you can reply me in letter after your thinking as well. It's not required that you have to reply as of now. Okay, you can reply it back as well. Okay.
Okay, yeah, thank
Okay.
you.
Thanks for your presentation.
All right then. Any other question?
If there is no one, am I allowed to ask one additional one to Shi Yuan? Because I
Yes.
just
Yeah.
was thinking about another slide, because you showed in your modeling work, there was just on the oil based, in which you showed there is like P wave density and something, and then there is if I remember, compositional model in which you are like having this interaction. So by this, and then there is another graph in which you are showing the supercritical values with temperature and this different one. Is it
Yeah.
like, do you also like with your modeling, you try to come up with some of the graphs that as the interaction increases and the more CO2 you inject, then this is like some range of pressure that you expect, that what it should be. And then when you are modeling with your acoustic approximation, so one value is this from your model, and then I guess there should be some boreholes active where you can have like a pressure readings, and you can like kind of cross check them and like approximate them. You do anything like this from your work?
So, the simple answer is that this sensitivity work would be done prior to me doing the simulation to seismic modeling work, cause that would be done prior to that. And your question is that if I do any sensitivity testings for like to understand the pressure and temperature changes for the CO2, right? And how it affects my elastic property.
Yeah, like kind of, yeah, because you are mainly in the acoustic approximation, so probably that could be like one way. And also I think it might be helpful to like QC your result. Yeah, like what you are getting from a simple approximation and what is
Yeah.
happening. Yeah.
Yep. So, we have done that within the group. We have QC'd our approximations against the equation of state which we hold as ground truth. So all the approximations that we use, which I mentioned earlier about the empirical relations, all of these have been, and the range of our pressure and temperature, mean max pressure and temperature, and temperature, well, it stays, the same because it's not a thermal model. We have QC that, and they all sit within 5% or less than 5% of the equation of state, which we hold as ground truth. So this has been QC'd further, but in terms of running the sensitivity on a 3D simulation to seismic scale, I have not done that, simply because they would be, what do you call it? There's two types of sensitivity to do it. One, it's if I get a range of simulation models with different low, mid, high case, which I only have the base case. And the other part is that I would think is that the seismic modeling case. So I don't think, because I've already verified and confirmed that the acoustic approximations are within our tolerance level, so I didn't further approximate within the petroleum modeling phase or the acoustic phase, if that makes sense.
Yes, certainly. Thank you.
Thank you.
Thanks.
Thank you, Shi Yuan. No more questions?
I think Noor has one last question.
Okay.
What role does 4D seismic play in ensuring long-term integrity? I
safety.
think, yeah. So my take on this is that 4D seismic plays a role. Perhaps the more important question or the more important task that what do you call it? That we should bear in mind is that 4D is the monitor part of 4D is just as important as the baseline part of 4D. You need a baseline before you can do a monitor, which means that a lot of companies have a lot of exploration seismic, which they acquired before production, and then they produce for 20, 30 years, however long, and then they want to start doing CO2 injection, which I think it would only make sense to have acquire a baseline pre-CO2 injection, just so you understand what the reservoir is, like how has depletion changed your reservoir, how has hydrocarbon production changed your reservoir, and then that will be your baseline. So I personally would think that a 3D seismic is needed. It's probably crucial, and then the 4D part is the monitoring part, right? So like you have your baseline already, that's 3D. Then you have your 4D. So I think that the 4D aspect of it, in my opinion, it plays a role, but whether or not it's seismic or it's a different technology, that will go back again to whether it's the cost versus value and the objectives of the operator and if they receive government support, etc. Yeah, but I do think that 4D seismic would play a role. How much of a role? It's uncertain until we see more from the upcoming projects in the next few years, which I'm honestly quite excited for them to start commencing CO2 injection. Hopefully that answers the question.
Thank you, Shi Yuan. I think that there's no more question from the attendees, so it is time to close the session. Thank you so much, Bridge, for being here today. Thank you, Shi Yuan, for this amazing talk. If suddenly you have any other comment, question, suggestions, you can always reach at us through the community email. Or otherwise, we will send you some information through the email you register for this webinar. So this is it from our end. Looking forward to seeing you in our next webinar. Hopefully we will be held in May, but for sure we will keep you all posted. Thank you so much. Have a nice rest of the day and looking forward to seeing you soon. Thank you, Bridge. Thank you, Shi Yuan. Good to see you.
Thank you, everyone.
Thank you.
Thank you, Maria. Thank you, everyone.
Thank you. Bye-bye.